Hello and welcome to the 60th lecture in this series. So let's continue our discussion of differential forms and the various operations associated with them. So one thing which we had for vector spaces was we could pull back differential whenever we have a linear transformation between two vector spaces. It gives rise to a pullback linear transformation from the corresponding spaces of alternating forms, and we can do the same thing when we have a smooth map between manifolds. The derivative is a linear map, and so we can use that to define this F star omega for any k form omega on the target. But as we saw last time, smoothness becomes a bit of an issue if you try to work directly with that definition. But in terms of local coordinates, it becomes quite easy to see this. So let's do that. So let u phi vc be charts on M and N with P in U, f of P in V, with P in U and more than f of P in V, I want to say that the whole thing f of U itself contained in V charts on M and N with this property. So let's denote coordinates on this. So this is M and N, and I have a map F here, U, V. So these coordinates here I'll denote by x1 up to xn, and here y1 up to ym. I mean, they're the coordinates of the corresponding Euclidean spaces with P in U and f of U in V, right? So now what we can do, so omega is now a form. Omega is in form 1, K form 1 N. I'll restrict omega to this chart V. Omega restricted to V, I know can be written as A I d y I, where A I are smooth functions, C infinity V. Now let's apply the pullback map. Vstar omega. I'll drop the restricted notation. So let me just write Vstar omega would be Vstar of AI dyi. Vstar of AI dyi, this would be let me look at a more general thing where phi star suppose I have something like this. F is a C infinity function on N, omega is a K form on N. I claim that this is the same as F composed with phi multiplied by phi star omega. Oh, sorry, F composed with phi, yeah, that's correct. F composed with phi star omega. And the reason is it's just that, after all, what is this? Vstar of f omega at this form at a point P is by definition d phi at P star f omega. Now d phi at P, this thing here, after all, d phi P is a linear map from TPM to TO. Yeah, that's fine. So T phi of P n. So the corresponding form here is being considered at phi of P. Now, even though I didn't mention it earlier, just like for vector fields, if you have a differential k form, you can multiply it with a smooth function and get another differential k form. And here f omega is its value at a point is just f of p times omega at p. Do the obvious thing. So here what I'll be getting is f of phi of p omega at phi of p. Now this is just a constant f of phi of p, so that comes out, and then I'm left with d star omega at phi of p. So this is f if I drop the dependence on p, convenient way of writing it is phi star omega f omega is f composed with phi times this is just phi star of omega. So that's how one gets this thing that I had here. So using that, here I get ai composed with phi and then phi star of dyi. So remember that we were trying to prove that phi star omega is a smooth form on M. This doesn't quite show it yet, but we are almost there, because to say that phi star omega is a smooth form, all I have to do is write phi star omega in terms of the standard basis for K forms, namely dxj. So let's do that. So here I would like to express this in terms of this dxj's, and then all one has to do is look at the coefficients of the final expression and claim that they are smooth functions on M, and then one would be done. Well, what is this? Dx phi star of dyi this will be some linear combination, so this will be some combination of CJ, but it will also depend on I, CJI dxj. So as usual, the CIJ are functions from U to R. For the moment, let's, I mean, if we already knew that, if we know that CIJ are smooth, we are done. We are done in the sense that we can get, we can show that Vstar Omega is smooth. So why? Well, it's just a matter of plugging in. So here the summation is over J. For each of these Vstar dyi, one has an expansion like this, and just go back and plug it in there. And what one gets is Vstar Omega equals summation over I as well as J. Now this thing is still sticking around, AI composed with phi. There is also this CIJ dxj. Now, as I said, if we know that CIJ are smooth, then in each, this is smooth. Well, AI composed with phi is smooth because phi, the map phi between manifolds is by assumption smooth. And, oh, oops, this is not F, this is phi. So, phi is smooth and the AI are smooth, therefore this composition would be a smooth function on U. And see, if we knew this CIJ are smooth, then the whole thing would be, this product would be smooth. So one would be done. Well, actually ideally one should write it as summation over J, then summation over I, AI composed with phi CIJ dxj. These are the coefficient functions one is interested in, and at any rate one will have to end up showing that CIJ have to be smooth. But what was CIJ? CIJ, we had F star, rather phi star dyi equal to CIJ dxj. This was the definition of this function CIJ. Now, as we have been doing all along, in order to get hold of these functions, all we have to do is evaluate both sides on So I want to show all of the CIJs are smooth. So let's do one thing. Fix I0 and J0. Evaluate both sides on J0 equal to on del by del x J1 del by del x Jk, where J0 equals J1 Jk. When we do that, all the terms in the sum disappear except one, the J0 when J equals J0, and that will be that will be phi star d by I. So then right, so this one evaluated on del by del x j1 del by del x jk, this is our CIJ naught. Actually I don't have to worry about fixing I naught, that's anyway fixed. The so for CIJ naught will be this, and I am interested in whether this thing is a smooth function or not, the left hand side. Well, what is this after all? This is this thing here, it's more of the same thing. So d by I, and then phi star just means I will be doing d phi of del by del x j1 etc. d phi of del by del x jk. That's what the left hand side is. Now the d phi of del by del x j1 will be it can be written as some linear combination of, so here we are working in local charts and so on, right? Yeah. So d phi of del by del x j1 etc. can be written as a linear combination of del by del y1. So I have to keep track of indices j11, j1n del by del yn. Now at this point, so one has to be a bit careful about where, so let's take a point P. So this is P. If I take a point P, this would be P, this would be P, and this thing is at P. Well, not so D, so this would be at phi of P yeah, so I would be pulling it back from phi of P, d phi at P, and this is at P, etc. This is fine. Right. Well, where was I? So yeah, so this is P and this is P. As I was saying, so this would be at P, this would be at phi of P, etc. So the fact that phi is a smooth map means that these coefficient functions a, j1, 1, etc., they are all smooth functions, a, j1, 1, etc. are all belong to C infinity U, since phi is smooth. Now it's quite straightforward, because as before, what one can do is one can just, in all these expressions here, one can plug in these corresponding expansions, use multilinearity, and then again use the action of dyi. We know exactly what it does to things like del by del y1, del by del y ik, etc. So we know that this is going to be either 0 or 1. So essentially this expression that I have here will be product of these A functions and then sum of products of these A functions. And since these are smooth, the overall thing is smooth. So it's actually, it looks a bit complicated, but it's nothing literally. One is using multilinearity at every step. So that proves that pullbacks, essentially pullbacks are smooth. That's all that we have done is proved that. Now we also have another thing we have is that regarding pullbacks, note if f from m to n alpha belongs to omega kn, beta belongs to omega ln, f star alpha wedge beta is f star alpha wedge f star beta. This is there's no proof needed for this, since it's a direct consequence of the corresponding property for vector spaces and linear transformations. So this continues to hold. Right. Now what I want to do next is something which does not, so far, other than the issue of smoothness, which did not arise for a vector space since there's only a single space involved. There's other things like exterior product, pullbacks, and so on. All of these, and the fact that we could get a basis for AK, the space of alternating forms, all of these things we directly carried over from vector spaces. The only new thing was smoothness. And in connection with smoothness, there is another important, perhaps the most important operation involving differential forms, which does not arise for in the context of vector spaces and linear transformations. So this is this notion of exterior differentiation. Exterior differentiation of differential forms. So what we are going to define a map, a linear map from omega km to omega k plus 1 m, which we denote by d. Strictly speaking, I should put a d subscript k because this map is defined. It obviously, when I just write d, there's a chance of confusion if I'm using different omega k plus 1 and omega k plus 2, I'll be still using the same d, but usually one doesn't put a subscript. So let's just follow the convention and write it like this. So this will be defined for each k between k greater than or equal to 0, less than or equal to n minus 1. Incidentally, I should mention that omega 0m is the space of 0 forms. Now, by convention, one takes it to be just the space of functions on M. And the reason for this convention actually has to do with this D operator. So according to what we are going to define, this D will take C infinity functions on M to 1 forms on M. And we already know how to do that. Given a C infinity function, I get a 1 form just by taking its derivative. So this D that we are going to define, when k equals 0, it will be exactly this operation, just taking derivative of functions. When k is more than greater than or equal to 1, then we have to do something new. And so let's the way we go about it is let me first give the statement, then we'll see. So theorem, maybe I'll write it in the next page. So this theorem asserts that there is a map D like this, which has various properties. So there are unique linear maps D from omega k m to omega k plus 1 m, satisfying for k equal to 0, D of f in omega 0 m equal to C infinity m is the derivative of f. In other words, whatever we had defined earlier, and D of a product now this D is supposed to be some kind of derivative. So whenever we have derivatives, we expect a product rule. So here it takes this form, d omega wedge eta plus, it's not quite the Leibniz rule, a sign comes into play, omega k omega wedge d eta, where omega belongs to omega Lm, eta belongs to omega Km. So only the sign of only the degree of the second term comes into play. Right. And a crucial property of this D, and the other crucial property is that D composed with D is 0. So this is omega k minus 1 to omega km to omega k plus 1 m I have a D here and a D here. As I said earlier, strictly speaking, they are different maps since they have different domains and so on. But if we use the same notation D for both, then what we want is that this map composed with this map, the resulting map is this. This map should be just identically the 0 map. Now this reason, this is kind of hard to explain if you think of D as a derivative operator. So if naively decomposed D would be the second derivative, and we would be saying that the second derivative of any k-1 form is 0, which doesn't quite make sense. So it's a somewhat subtle thing, but at any rate, D cannot be regarded as just a derivative in any usual sense. It's something more than that. In fact, the reason for the natural interpretation for this D composed with D arises from topology rather than the study of the study that we are engaged in right now. This also satisfies in a chart. D is given by, in a chart we know that every form can be written in this form, in this way, and then this is dAI wedge dxi. Remember, AI were functions, so dAI is a one form. So one form wedge, this dxi was already a k form, so this is a k plus 1 form. Then D is local, i.e. if omega equal to omega prime on U, then d omega equal to d omega prime on U. So it does not matter what omega and omega prime are outside U. If they happen to coincide on an open set, the D will also be the same. Then D of omega restricted to U. So here U is any open set. Same thing here, d omega restricted to U is d omega restricted to U. So I'll prove this next time. We'll first do the construction for Rn and then get it. All right, so we'll stop here.